Hi guys, my name is Boris and I am a computer engineering student currently in my 5th bachelor semester at the Technical University of Berlin. On this channel I want to talk about things that I've learned and might bring you value, a few educational topics and perhaps lifestyle videos. Now in this video I will continue the series where I take a look at the Technical University of Berlin and what you study here in your bachelor's degree for computer engineering. We'll take a look at the 3rd semester. Now, this semester will possibly be the hardest one. At least it was for me. In this semester you will have a course about semiconductors, and here the topics won't be that easy to understand in the beginning. And you will also have a course about distributed systems and computer networks, where the homework will be quite demanding. But after this semester, you will basically be in the flow of your uni life. So let's get started right away with your last official maths course. Now, this one is a mouthful. It's Integral Transformation and Partial Differential Equations, short ITPDE. Now, as you may have noticed, I haven't mentioned this course in the intro, and this is because the maths isn't that hard. Like, this course in particular is the definition of or at least as I call it, a cookbook course. Okay, this course consists of 2 parts, integral transformation and differential equations. You should be starting with integral transformations, and that means you will be learning what a transformation is and what the purpose of it is. Now, the transformations that you will be mainly learning are the Laplace and the Fourier transformation, but also a bit about the Z transformation. So the Laplace transformation is mainly used for differential equations, but a bit simpler ones. And the Fourier transformation is used, or rather the maths in the Fourier space in which you will land after a Fourier transformation, is in particular important for signal theory, since you will learn about that. It represents the frequencies a signal consists if you transform that signal. Now, these transformations will basically again be formulas, how to do the transformations that will be on your cheat sheet, and you will really only have to practice and use them a bit so you get faster while doing so. Next, you will be looking at a thing called convolution. This is a new operation concerning 2 functions where you basically push the one function through the other function, and the resulting function will be the area that overlaps between the 2 functions that move through each other. Now, you should focus quite a bit here because it can be quite confusing. Next up in the transformation section will be LTI systems, linear time invariant systems, where you will again be looking at system functions, remember electrical networks, and you will basically be using Laplace transformation, but also a bit of Z transformation to solve those. Okay, that's basically it for the transformation part. Now, to the differential equations part, I would really like to only scratch the topics a bit on the surface, since you will be learning those and they are pretty cool, to be honest, but you won't really be using those on your ongoing, and it would take a few minutes to explain those. But you will be learning about linear differential equations of 1st order with variable coefficients, and you will be learning about linear differential equations of the 1st order with in a linear system where you have variable coefficient matrices, and those matrices can have different properties which will help you solve the problems and use specific algorithms to solve those. Continuing with normal scalar linear differential equations of the order n, and in the end there will be solving of partial differential equations, where, for example, one of the most famous ones is the Schrödinger equation. Okay, so although this all sounds pretty insane maybe, It is really fun because the maths has a very systematic approach. You will have really a step-by-step algorithm that how to solve those differential equations, for example. And this is pretty fun because you will be writing like 3 sheets of paper full of maths, and it looks insane, but the maths itself isn't that hard. The thing is, you should be aware of what you're actually calculating and for what you're using it, because you might lose track of it, or at least I sometimes did. Now I would like to continue with the course Signals and Systems, where basically the whole entire transformation stuff that you will learn in the maths course will be relevant. So you will be learning both in parallel, and that's basically just a bonus for you. Starting again with convolution. Now, here in this course, you will be really going a bit more into depth in this topic and do a few more examples and really a bit more complex examples, because this will be one of the biggest topics or focuses of this course. So try to keep up and focus on this one, and you'll have a pretty big advantage if you understand them. Next up, you will be looking at a big system that consists of little systems. System is an abstract term, which basically means that there will be a system function for each little system, and you'll be looking at what the output y of t will be when you have an input x of t that goes through a system with lots of little transfer functions. Here you'll also learn what a Dirac delta impulse is, or a Dirac comb, and you will learn how a system reacts to those. So imagine you have a electrical system, a little circuit, and you turn on the power supply. The voltage that you apply spikes very hard. It will rise very fast, and it will resemble basically a Dirac delta impulse. For a bit of real-world context, I was really going through all of my notes, and you will really be doing a lot of convolutions. But you will also learn how to represent a system function in a new way, where you can filter out different properties which describe a system function. All of these calculations are based on time-continuous inputs, but you will also learn how to do those with time discrete systems, so where all the values that a input may have are separated and are not continuous, basically. And we're done. Now, the professor is a really cool guy. Like, cool, he's in terms of standing in front of the whole students with one hand in his jeans and just talking about topics and talking about his nice Mercedes Benz. But although he is a really cool guy, don't think that he'll go easy on you in the exam. This one, he really tricked some of us by playing the cool guy, but then the exam was quite stressful. You really didn't have quite a lot of time to think. You really had to know everything like in the instant. So I would really recommend you to exercise a lot and try to get fast and in solving those calculations and convolutions. Okay, now let's get to the hard part. We'll be talking about semiconductors, or rather semiconductor components. Now, by hard, I don't mean like that you have to do a lot of work, but rather it's hard to understand. You'll be talking about band theory. So how a electron jumps into a energetically higher state, and how the material affects this energy that's required for the electron to jump into a higher state. And well, that's resembled in a wider band gap and so on. Now, that all is very fundamental theoretical physics and quantum physics that you will have to get through. Don't get me wrong, it's really, really interesting, but I don't really think that the professors do a really good job in explaining those. So I really recommend, or I would recommend watching a few tutorials or really ask the tutors. They will most likely be your savior. You'll get bombarded by thousands of constants and formulas, and I really recommend keeping track of those, like, I don't know, writing them down on a sheet of paper, because the professors will work with the formulas and there will be a few constants or other definitions in those formulas, and they won't bother explaining those too much. So try to note them down and keep track of those so you don't get lost in the formulas. Now, up until there, this will be the hardest part. But if you really understand this band theory or band model, it will ease up quite a bit. You'll continue finally to semiconductors and what doping a semiconductor is. And with that, you will learn what a diode is and how a diode works. And all of that will be explained based on the band model. So you really have to have understood that at this point. You will go into detail into a thing called current voltage characteristic of a diode and what effects light and temperature might possibly have on the diode, or rather the semiconductor. Continuing, you'll get to the transistors, which are also semiconductor components. And you'll be focusing on basically two of the transistors. The most popular one, the MOSFET, the metal oxide semiconductor field effect transistor, and the bipolar transistor. Here you will also go into the different current voltage characteristics, since in such a non-linear electrical component, you have different voltages inside of the component itself. So with that, you will have additionally also a few formulas. And yeah, that's basically it. Now, I really want you to try to understand the band model as early as possible, since the professors will really just go on and work with that and not try or not bother to explain them this model too often, and it is really necessary. Now, next to the lectures, you will have lab visits, and those will basically be your tutorials, and I really want you to embrace those lab visits or tutorials where you will be talking to your tutor. And I really don't think that I'm over-exaggerating when I say that pretty much the tutorials or the lab visits really got me through the course and really helped me understand everything. Shout outs to my tutor Beej. And yeah, so when we're done with that, let's continue with the next course. Okay, to calm down a bit, we will take a look at the practical course of computer architecture. Remember the theoretical course in the first semester? Now, I don't really know how to translate it into English, because in German it's basically computer architecture internship, like Praktikum. But you really just stay in uni and apply your theoretically learned or gained knowledge. Now, here's not that much to talk about. It is a pretty simple 3 credits course where you implement your knowledge about processors in a language called VHDL, which is a hardware description language. You won't need any crazy algorithmic knowledge. You really just have to read the tasks that they give you, and you may need to pay attention to what your tutor says. He will sum up the theory that you will need for the tasks, and with that you should get the problem solved quite easily. Now, I want to mention that since this is a practical course, the grade that you get in this course won't go into your final grade when you finish your bachelor's degrees. Other courses like that will be your operating system course or the hardware practical course, and the courses that you choose in your free choice courses. Oh, and there also, which is quite interesting, Your first maths courses, Calculus 1 and Algebra 1, also won't be calculated into the final grade. But to be sure that applies also for your semester, you should take a look at the regulations yourself, and I will put the link into the description below, and you should find it under the point 8. Okay, this is the last one. Computer networks and distributed systems. Now, here I said that you will have to do a lot of work. The content of the course itself is not that hard, and it's really interesting actually. But the homework assignments, they might get you. In the beginning, you will learn a few calculations regarding the communication speed or how long a package of information will take to get to its destination. And you will get started with the ISO OSI model and learn what TCP and UDP are. Now, in conjunction to the lectures, you will have to read through the materials they provide you to be able to solve the homeworks, where you'll have to implement basically a client-server communication that is based on sockets. Now, I know that sounds kind of strange for the beginning, but you will really need to read through the guide they provide you. I think it's called Beej's Guide for Network Programming. I will provide you the link in the description below, but they should also provide you the link for that, and you will probably need it, except you have basically already acquired knowledge to do such implementations. In that case, good for you. You will learn about a few supporting mechanisms such as a RPC, what the DNS is, and what transparency means in regards to computing. Now you will learn about distributed hash tables and peer-to-peer communication, and regarding that, about a chord ring. Now this should be a pretty major part in your homework assignment. Now, a chord ring is a structure of nodes, where the nodes are computers or servers that have information distributed among them. Now, those servers only know the successor and the predecessor in the ring. And then the question is, okay, when a request comes to a specific server to get information, how does the request propagate through the ring to receive the information that the request needs? And another question is, what happens if a new server wants to join such a ring, and so on. You will learn about HTTP, the Hypertext Transfer Protocol, and what REST means. And you will also learn about time synchronization between different devices. And with that, you should learn 2 ways of doing so. Again, that will be just protocols and algorithms that you will learn, not really complicated ones. So you will basically go along the entire ISO OSI model and go through all the layers and learn about routing and switches, what NAT is, and how basically the request or the information propagates through the different layers and arrives at its destination through routing and switches. At this point, you should have gone through the entire model, and now you will focus on package loss. So what happens if a package gets lost, or what happens if the data in a package of information changes. For that, you will learn a procedure called go back N. And we're done. As mentioned, the content is really interesting, for at least again for me, and you will basically learn how the entire communication in the internet, or basically in all networks, work over protocols, in specific now the internet communication with the ISO OSI model. And you will really get to appreciate the internet more. But really the difficult thing is the homework assignments, or rather the time-consuming part, in which you will start by building up a basic server-client communication through TCP or UDP. I think it should be TCP. and implement a cord ring of multiple servers and then try to request informations or update data in a specific server. And you will have to implement another server joining the cord. And yeah, the focus is implementing the cord ring functionality. All this will probably take a bit longer than you think, so don't try and push the assignments to the last minute, and try to start the homework pretty early on, and you will have access to the tutors and ask them questions. And that will be pretty hard when you start your assignment 2 days before the deadline. For the lectures, go to the tutorials, pay attention there, do a few exercises, and you really should be pretty set for the exam. Okay, and we're done with semester 3. Overall, a pretty rough and intense, but also really interesting semester. So if you put in the work and try to have as much fun as possible, you will be able to get quite good results. And with that said, I really wish you a lot of fun while learning, and stay excited, and you can be excited for the following semesters. And thank you very much for watching, and see you in the next one. Bye!